How does the yellow show up? Shows up pretty well. So in terms of grading, I've gotten a few assignments graded. Some assignments, so I've gotten 1.1, 9.1, 9.2 graded, and the solutions have been made. I need to make solutions for 9.3, 9.4, 9.5, 9.6, and 9.7. I remember saying it would all be graded by the weekend was over unless some catastrophe occurred. And such catastrophe did occur. My wife and I have moved from an apartment to a home, and we're trying to get our deposit from the apartment. And the upstairs residence, for some reason, has some leak, and their leak came down into our apartment. And so we spent all of Saturday, literally from 8 a.m. to 9 p.m. cleaning that place up, hoping to get a deposit. So throughout this week, I'll work to get you your feedback. And thankfully, your test has been moved. It won't be this Wednesday, but next Wednesday. Right? That's really good, because then you'll have time to get your feedback and absorb it. Also, whenever you send me online versions of your work, don't use Cam Scanner. That thing has a link that expires after a week. And
I switched it to where I have my email set up, and I sent it to you again. I think you should have a PDF now.
That would be great. Yeah, just send PDFs or JPEG pictures, even like taking your cell phone out and taking a picture of it, as long as it's not too hard to read, that's perfectly fine. That's perfectly fine. Because that way it doesn't just like the link doesn't expire. I can access it whenever. That's the only thing. Cam Scanner is probably a really nice app, but you know, they have storage issues. They can't store everybody's data forever, so they'll delete it after some time. And so that's just what happens. And I don't always look at it right when I get it, and I don't. So that's what happened. From now on, either do a paper copy or like a file that isn't expirable. And yeah, I have the solutions for 9.1, 9.2. I'll be uploading those soon. And the solutions for the rest of them, I'll generate them and upload them and grade your assignments and hand them back to you. In terms of feedback, the assignments will only have like minor feedback and a score. And if you're wondering what I did wrong, you can first look at the solutions. Any deviation from the solutions is something like that will technically be the reason for the deduction of points. And you can always ask me about it via email or in person. Yes, ma'am.
If we turn in a paper copy, are we going to get those back?
Yes, yes. I actually have some of them right now. I could hand them back, but I'm not going to because I want to hand them back all at once. So I will upload the solutions. So it really won't matter because some of the grades have been uploaded, if you guys have noticed on Canvas.
Yeah, I'm just thinking for like math ed majors, we have to keep a portfolio of
Oh, yeah.
our papers and our grades and stuff. So I didn't know.
Yeah, you'll get it back, just not today.
Yeah, that's fair.
Like my folder's so like unorganized, I'd probably have to spend 5 minutes digging them out. So that's the reason for that. Besides that, I would have handed them out. Also, like let's say you did it online, right? You turned in a picture. There would be no marks on that picture. You just get a score associated to that picture. And then you could look at the solutions to see where did I deviate? Where did my solutions deviate from the published solutions? And that's how you determine what you got wrong, you know? So that's how I like to do things. One, I like to do the homework too, just like you guys. Like when I assign the problems, usually they're problems that I want to do, that I find interesting. Like there was one problem where it was like, prove this really cool thing, and I was like, I want to do that. So I like doing the homework just as much as you guys. So yeah, you guys gotta give me some time to catch up to you guys. I'm a little behind from you guys. I gotta catch up to you. I will catch up very fast though. I've taken this class before. I'll catch up quick. So let's move on to 9.7. There's a lot of stuff in this section. There's cylindrical coordinates, spherical coordinates, polar coordinates. Let's right off the bat start off with polar coordinates. Let's say we have an x and a y. All right, we could use rectangular coordinates where we say, okay, if this is at some A, this is at some B, we can call this, oh, this is the ordered pair A, B. All right, that's one way to do it. This is called rectangular coordinates. Another way to do it is to say, you know what, that's nice and dandy, but you know what, there's another way of doing it. There's another way of doing it with two pieces of information. Before, it was an x and a y. Now it could be an r and an associated theta. So this point is r theta. Just like some distance away from the origin and some angle. So before rectangular coordinates, you had some x, y, and in 3 dimensions, you'll have some x, y, z. Then you can move to polar coordinates, where you'll have some r theta, and guess what? Z. So notice that we can create a right triangle. If I do a vertical projection over here, and notice that the sine of theta, if I call this y, call this x, that sine of theta is opposite over hypotenuse. So notice that I can create a transformation equation for y, and that's r sine of theta. Similarly for cosine of theta is adjacent over hypotenuse. I can create a transformation equation for x. So now I know how I can transform from x, y, z to r theta z. There's no z because we don't need the z. Z is z. There's no transformation for z in polar. There will be transformations for z in spherical, as you guys will see. But notice that the way to determine r is just the Pythagorean theorem applied to this triangle. So here's an example. Convert the point 2, 3 into polar coordinates. Notice that we're given that x is equal to 2, y is equal to 3. All right. And by the transformation equation, we know this is equal to r cosine of theta, and this is equal to r sine of theta. But unfortunately, we don't know r and we don't know theta. But we do know r is equal to this. So we can determine r. R is equal to the square root of 2 squared plus 3 squared. Notice that this equals square root of 4 plus 9, which is equal to root 13. Aha! That's what my r is. So this equals root 13 plus sine of theta. This equals root 13 sine of theta. So we're almost done. Still don't know what theta is, but we'll figure it out. Okay, the way we can find theta is in a multitude of different ways. We can either solve for theta using cosine inverse, or sine inverse, or tangent inverse, actually. Another way to do it is to take sine of theta over cosine of theta, which is equal to tangent of theta, which in the triangle is y over x, which then you can say that's 2 over 3. And you could also say that that is these guys as well. The root 13s cancel, and you'd get the same result. Okay. So then to solve for theta, you just take the tangent inverse. And that's what theta is. Whatever your calculator outputs for that, that's what you get. We can plug it into a calculator and maybe get the degrees. But I'll do another problem where I know the actual value. That may not be a tangible value. So here's another one with a tangible value. So I actually didn't highlight this point enough. So remember when I said that this is our polar representation, here's the x, here's y, here's the theta, here's the r, and I said, well, this is a 2D version, and you transform it into a 3D version, right? This is called polar. Whenever you transform it to a 3D version, this becomes cylindrical. Okay, that's because if z is free, then it can rotate at any value of z with a fixed r and theta. So it will form a cylinder. Okay. So now let's move from polar, let's say, to cylindrical. So let's say I have a 2 pi over 3, and I have a 1. And let's say I want to convert this to rectangular coordinates. Notice that this is an r, a theta, and a z. I want it to convert it to an x, y, z.
So Z doesn't change.
No, it doesn't. The transformation equation for x dictated by the cosine function is this. The transformation equation for the y dictated by the sine function is this. The transformation for the z is the trivial transformation, the identity transformation. So, given this piece of information, we have r is equal to 2, theta is equal to 2 pi over 3, and z is equal to 1. So, utilizing our transformation equations here, on my left and your left, right here, let's start to transform polar to rectangular. Okay, I want to know what x, y, and z is. I already found z, we're done. Z is trivial. Let's find x. Oh, well, to find x, I need r, and to find y, I need r, but I also need theta. I already have theta. Theta is known, so I only need to find r. If only I knew a transformation equation for r. Ah, we got it. But the thing is, we don't know what x and y is, so how can I find r? Well, we know what theta is, right? So x is equal to r cosine of our theta, 2 pi over 3. Y is equal to r sine of our theta, 2 pi over 3. Who knows what the sine and cosine of 2 pi over 3 is? On the unit circle, this is pi over 2. 2 pi over 3 is right here. It's the next special angle whenever you add pi over 6 to pi over 2. Meaning, it assumes the x value, negative 1/2, and the y value, positive root 3 over 2. You guys remember that? Okay. So now that we know this, we know that x is equal to negative r over 2, and y is equal to r root 3 all over 2. We're stuck. I don't know x because I don't know r. I can't find r because I don't know x and y. Let's just give up. What? We don't have to give up? Wait, what? You can utilize a tangent function to eliminate the ratio of r and r that is a mutual ratio in sine and cosine? Oh, that's a great idea. What if I were to take the tangent of theta? That's y over x, right? But substituting those values, this is r root 3 over 2 divided by r times the negative 1/2. R's cancel. Now I have a pure number. All right? Multiplying by reciprocals, the 2's cancel, so I get this is equal to a negative root 3. Did I do that right? I'm pretty sleepy right now. Catch me if I'm wrong. So moving to calculation over here, being sleepy is not an excuse. What is this? You gotta perform. It doesn't matter. That's how it is. So then theta is equal to tangent inverse of negative square root of 3. Whoa. But we know theta, don't we? We want to know x and y. We aspire to find x and y. So what we need to do is find r. Have we found it yet? No, we haven't. But we did find that x is equal to this, right? And that y is equal to this, right? So what happens if I just plug it in into this equation? R is equal to the square root of x squared plus y squared. Let's see if something happens for us. R is equal to 2. Let's put this out here. So what's going to happen if we plug it in just there? So actually, before I do this, let me reveal it to you in a different way. Notice that x squared plus y squared should equal r squared, correct? Notice that x is equal to r cosine of theta. Y is equal to r sine of theta. But let's just plug in our numbers now. So notice that x would be equal to that entity. And y will equal this entity. Root 3 over 2 here. When you square them, notice that you're going to get this r squared term, and you're going to get a 1/4 here. You get this r squared term, you get a 3 over 4 here. You can factor out r squared, and you get 1/4 plus 3 over 4, and you trivially get r squared is equal to r squared. So how can I find the pure value for x, and how can I find the pure value for y? Guys, we've been going on.
That's why I was confused.
We've been knowing R. So to find x, all you gotta do is plug a 2 here. So x is your -1. Don't allow people who like want to like wave their arms and be all fancy schmancy to make you forget what's going on here. Life lessons. So we know x, we know y, we know z. What is my x? That's -1. What is my y? That's root 3. And what is my z?
1.
Yeah. Okay. What can I erase? I should probably erase this stuff here. Now, let's go from rectangular to cylindrical. Here's our x, y, z, convert it to an r, theta, z. So I don't know what it is yet. Yes.
So on that last question,
Uh-huh.
the tangent, what do we do that for?
That was, you could have solved it that way. So I took the tangent of theta is equal to y over x. We knew what y was, this, and we knew what x was, this. That was to reveal to you that you can get rid of r if you didn't know it. But we didn't know it. It was unnecessary. But let's say you didn't know it. I could have generated a problem where r was not given to you. And you could have solved it using that technique. But r was given to you. Well, it's good to know what you can do, right?
I just wasn't sure what it was.
Yes, yeah. Not gonna lie, that wasn't the most clear cut presentation of that example that I've ever. That was probably one of the more confusing ways to explain it. So it is not. It's not surprising that you guys are kind of scratching your heads right now. But we'll work to fix that. Let's convert this from rectangular to polar. Okay, so we still have the transformation equations. And don't forget z is equal to z. So z is done because this implies that z is equal to -7. We're already 1/3 there. All we got to do now is find theta and r. R is pretty simple. Just use this. So I get x squared, which is 3 squared, plus y squared, which is -3 squared. This is equal to the square root of 9 plus 9, square root of 18. Does this break down anymore? That equals square root of 2 times 9. Yeah, this becomes 3 root 2. So our r becomes a 3 root 2. So I know what z is, it's a -7. I know what r is, it's a 3 root 2. Any questions so far? Okay. All right. So now all that remains is theta. We know r, we know x, we can find theta. All right. We can either use the tangent or the cosine or the sine inverse. All right. Because I introduced tangent, why not talk about it? Tangent of theta is equal to y over x. And that's equal to sine of theta over cosine of theta. Okay, but I know what y over x is. It's that -3 over +3. So this is equal to a -1, and that's equal to my tangent. So to find theta, I take the tangent inverse of both sides to find the -1. We go on the unit circle. We try and determine what the tangent inverse of -1 really implies. We notice that here at pi over 4, tangent is 1. Also here at its adding pi plus pi over 4 is 5 pi over 4 over here. Tangent inverse of 1 would be equal to pi over 4. Tangent inverse of 1 will equal 5 pi over 4. But we're looking for -1. So then that must occur either here or here. This is pi over 2. This is pi over 2 plus pi over 4. What's that number? It's 2 pi plus pi all over 4. That's 3 pi all over 4. That's 3 pi all over 4. And then over here, we got to add a pi over here to find out the other spot. So it's 3 pi all over 4 plus a pi. That's equal to 7 pi all over 4. This is 7 pi all over 4. So it's at these values that it will equal a -1. So which one is it? Well, it needs to be the one that has positive x and -y. Because what do our coordinates have? Positive x and -y, right? So we need to take this one to tink. Remember, these guys are tangent inverse of pi over 4 and tangent inverse of 5 pi over 4 is equal to +1. Remember that? But the tangent inverse of 3 pi over 4 and 7 pi over 4 equals -1. So we must discern which one should we pick. So theta should equal this 7 pi over 4. For it to have positive x and negative y. Less nebulous of an explanation, right? Yeah, guys, my bad on that first one. I don't know what's going on. Might be because I stayed up till 3 in the morning last night and woke up at 6 today. It is what it is, man.
It is what it is.
It is what it is. You can't make excuses. But I will tell you all, sleep is very important. The only reason I'm not sleeping is because I have no choice. I would be sleeping 12 hours a day if I could. Okay. Now, let's talk about the advantages of cylindrical coordinates. The advantages of cylindrical coordinates, I'm not going to even write anything on the board, okay? It's advantageous to talk about, to use cylindrical coordinates whenever your problems relate to axes of symmetry about the z. Any problem that has z-axis symmetry, use cylindrical coordinates because it'll be easier. The calculations will be easier. Okay? All right. So here's a cool thing I'm just going to mention real fast and move on. What does the function y equals x give us in R2?
Straight line,
Yeah, it's just like your very prototypical straight line.
45-degree angle.
Yeah, exactly. But our function, notice that a function f of xy is equal to z would generate this. A cone, because it's like that line, right? Y equals x, it's like that line, but you get the line and you rotate it about the z. So it would sweep out a cone, both a cone on top, intercepting in the vertex, and a cone on bottom. I just thought I'd mention that. It's in your text, and it's very interesting. And you guys know about rotating shapes by now. Okay. Spherical coordinates. Spherical coordinates. Okay. Before we had an x, y, and a z, but we want to convert it to a new way. A theta, phi. Wait, no. Rho, theta, and phi. Okay. So here's spherical. It's just another way to locate a point in 3 dimensions. Okay, so here's my rho. Okay, so this rho, notice that there's this angle right here. All right, from here to here, this angle, this is a theta. And then we have this angle right here, which is phi. Basically, what I'm trying to say is phi is the angle between the z-axis and your rho. Okay, and theta is the angle between your x-axis and your rho. Okay. Notice that phi can only range 180 degrees, but that theta can sweep all 360 or 2 pi. Make sense? Because, you know, the z-axis runs out. But whenever theta measures basically in the xy plane, how much does it deviate from x in the xy plane? And oh my freaking goodness, I would love to derive the transformation equations for you. It's actually pretty easy. It's the application of sine and cosine to two different triangles. I'm going to save that for a YouTube video. We have to get through this whole book from 9 to the end of the book. So I will show you the stuff, but it will be on YouTube. In lecture, I will give you the essentials. So our transformation equation for x now becomes rho sine of phi cosine of theta. It becomes so apparent when you derive it. This becomes rho sine of phi sine of theta, and z becomes rho cosine of phi. With rho squared, E is equal to x squared plus y squared plus z squared, because you were talking about spherical coordinates, which is this is a point on a sphere. So that P is a point on a sphere, so of course rho is going to indicate its radius. And if that's your sphere centered at 0, centered at the origin, you're going to get this equation. It's the standard equation of a sphere centered at the origin. So now, let's convert between spherical and rectangular. Let's say I'm given a 2, a pi over 4, and a pi over 3. Let's convert that to x, y, z. Ooh. Yes, ma'am.
Just to clarify, y has two signs, not a sine and a cosine.
Just to clarify, y has two signs. Yes, the sine of the angle phi and the sine of the angle theta. Isn't that cool? It becomes apparent in the derivation. If I were to derive it to you, you'd see exactly why that's the case. It's just the Pythagorean theorem multiplied to two different triangles. Not multiplied, applied to two different triangles. All right? You have a question?
No, I just said okay.
Oh, you said okay. Okay. So, time to convert. Remember, this is a rho, a theta, and a phi. So we have transformation equations. I really can't do rho yet because I need a x, y, and a z. That's kind of going to have to be at the end here. Okay? But I can do x and y and z separately, and at the end calculate rho, right? So let's do x. X is equal to rho, which is my 2, sine of phi, which is pi over 3, cosine of theta, which is pi over 4. So this is 2 times, what's the sine of pi over 3? What's the sine of pi over 3? No calculator needed. No. Yes. What's the sine of pi over 4? That one's really easy. Yes, ma'am. So then I get x is equal, one of the 2's cancel here. The tops can multiply, so that becomes root 3, root 2, which is the same thing as root 6 over 2. This is my x. Now let's do y. This is equal to r, or rho. Rho sine of your phi, sine of your theta. What is the sine of pi over 3? Yes, ma'am. What is the cosine of pi over 3? Or, oh, no. What is the sine of pi over 4? You already said it. So 2's cancel. So then, guess what I get here? Why is this happening? Why are they getting the same results? Well, it's a consequence of the fact that the sine of pi over 4 and the cosine of pi over 4 are the same. And It's a consequence of the fact that over here, the sine of phi is repeated, and phi stays pi over 3. So the only way to get these values to change is to get theta to change from that. Okay. So are we done? You know what? What was that?
The Z.
The Z. The Z? What do you mean the row? I need to find rho. Oh, we need to find Z.
Rectangular.
Oh, yeah, you're right. And here's this equation, because we know rho, don't we? Mm-hmm. Z is equal to your rho cosine of phi. And you know your rho, remember? Cosine of your phi. Which one of these is phi?
Pi over 3.
Uh-huh. So this is 2 times what? What's the cosine of pi over 3? Yes! There we go. So this gets converted to excellent. So now let's go the other way. Let's go from rectangular to spherical. We went from spherical to rectangular. Now let's go from rectangular to spherical. This is 1, 2, 3. Let's convert it to a rho theta e. We have our transformation equations here. That's all we need to convert and do this problem. Notice that, unlike last time, the way to start is to use this, because really this is the only thing we can do right off the bat. We can't even do this z part because it requires rho. So really, right off the bat, we need to start off with this one. So we know rho will equal to the square root of 1 squared plus 2 squared plus 3 squared. So then rho is equal to the square root of 1 plus 4 plus 9. Rho is equal to the square root of 14. This 2 times 7, it doesn't break down any further. So we know what rho is. Now we can find what? Our best bet is to find phi, because this equation, we have 2 knowns and 1 unknown variable. We know rho and we know z. We know z is 3. And so we can solve for phi here. So this is our best start. These guys, we couldn't use them because although we know y and now we know rho, we don't know phi and we don't know theta. So we'd be trying to solve an equation with 2 unknowns, and we know algebra doesn't have the tools necessary yet to do that. Human beings have not invented the tools to do that yet. Maybe the tools just don't exist. Who knows? Maybe they do exist. But z, which is equal to 3, is equal to rho, equal to root 14, sine or cosine of phi. Okay, so I can solve for phi. What I do is I get 3 divided by square root of 14, and I take the cosine inverse of that. This is my phi. And whenever you plug it into your handy dandy calculator, that becomes approximately 36.69 degrees. Now, we can stick 36.69 over here. What goes for theta? Which one of these should we use here? So again, this is where we can use tangent to make our lives simpler. Tangent of theta is equal to y over x. And that's equal to all of this over all of this. But notice they have two things in common. They have a rho and a sine of phi. So you can cancel those out. So all you'll get is sine of theta over cosine of theta. Okay, which is what we have so far. But we know y and x, and that's equal to 2 over 1, right? So it's just theta is a tangent inverse of 2. Another way you could have did it. Another way you could have did it was solve for sine, because I keep using tangent. But actually, I'm thinking if you plug tangent inverse of 2 into your calculator, it will read an error, won't it? Someone who has a calculator out, plug in a tangent inverse of 2. It will read an error because tangent, there is no angle on the unit circle that the tangent has value to. So it's gonna not. Is that correct?
I mean, I'm in degrees, but it gave me 60 degrees.
Okay. It might be defined for it. But let's say, you find something that is not defined for, you can always use these guys as well. So for instance, you could use this one. Let's use x. So this one, I would get 1 is equal to our rho. I'm just showing you all the different ways you can do things. Sine of phi, I know it's sine of 36.69. Cosine of theta, so I can solve for theta. Theta is equal to the cosine inverse of 1 over square root of 14 sine of 36.69. Okay, and that's another way to do it. It should be the same answer. Okay. And you could even do it sine inverse or cosine inverse or tangent inverse. They should be giving you the same values. Which is approximately 63.43. Jamie, do you agree? Mm-hmm. So let's talk about the advantages of using spherical coordinates. Again, the advantages of using spherical coordinates are that you can apply them to problems that have spherical symmetry. Oh, I thought I had to dodge that. Ooh. I thought I was going to have to dodge that. So notice that problems that have spherical symmetry, you get rho squared, which is equal to this. If you have a sphere, it equals to r squared, right? So you just get rho squared is equal to r squared. You get rho is equal to r. It's like a very simple equation. Whereas if you had to represent it in rectangular coordinates, it would be a very complicated equation. Okay, here. Now, We have like 7 minutes remaining. I can either derive the spherical coordinate transformation, but I told you I'll do that on YouTube. Or we can do a few more examples. And as you know, this is the last section on the first exam. So let's see here. Let's do another example. Let's do 0, 2 root 3, negative 2. I'm assuming that's, yeah, rectangular. Let's convert that to spherical. So I got my transformation equations over here. And I know that this is my x, this is my y, this is my z. I hope that's not my x. I'll run away. Okay. So let's start converting. Notice that, which one should we do first? Let's open for suggestions here. Which ones out of these should we determine first? I vote row, you know. We know all of the x, y's, and z's. Why not just do that, right? So rho will equal to the square root of the x component squared plus the y component squared plus the z component squared. So notice that this is equivalent to 2 times the 6, or nope, 4 times the 6, nope, 4 times 3 plus a 4. So this is equal to the square root of 12 plus 4, square root of 18, which is equal to, oh, it's 16? Oh yeah, thank you. So that's 2 times 8, which is 2 times 2 times 2 times 2. So what can I reduce this to? Yeah, it really breaks down to 4 times 4, right? Square root of that is 4. So we know our rho. What's my theta? All right, what's my phi? Which one should we find first? Yeah, with the equations we have to deal with, phi is our next choice. Because now we have rho, we have z, we can solve for phi. And we know z is negative 2. That's equal to rho, which is 4, cosine of phi. Phi, we don't know it yet, but we can solve for it. The cosine inverse of negative 2 over 4. So it's the cosine inverse of negative 1/2. At what angle on the unit circle does the cosine value assume a negative 1/2? Phi is precisely equal to 2 pi over 3. Right? So this needs to be a 2 pi over 3. What about theta?
That's a divide by 0.
Pardon me?
If you solve it using tangent, it's a divide by 0.
Yes, that's what I was pointing out earlier. Technically, the tangent inverse of 2 is not a valid question because there is no angle such that the tangent outputs a 2 because the tangent is Sine, cosine, and tangent are defined on the unit circle. So there is no angle that would output a length 2. The highest value of a length is 1, right? The highest value on the unit circle is 1. So it can't be equal to 2 technically. This is like an overly technical trigonometry point. But just letting you know, if something goes awry, just use the cosine or the sine, because then you won't be as Caleb is saying, you won't be divided by 0. I think I know everybody's name in here. It's Ivor, Caleb, Alexis, Jamie. Woo! So, how do we find theta? You don't want to divide by 0. Oh, you don't want, I say we use 0 here. Actually, I say we use this because 0 would then equal rho, which is 4, sine of phi, which is 2 pi over 3, cosine of theta, which is what we want to find, right? So, right?
Well, yeah, just
Divide everything out, you just get cosine of theta is equal to 0. Implies I just want to know what cosine of theta is equal to cosine inverse of 0. And what is that? At what angle does the cosine output no length? Pi over 2. And add a pi to what you just said. Pi plus pi over 2 is 3 pi over 2. Okay, so yeah, but which one? Because they both work, right? Pi over 2 works, 3 pi over 2 works.
Y is positive, so it's pi over 2.
Ah, y is positive, so it's pi over 2. I like that. That's how you're supposed to think about these things. Make sense? Good. I'm very proud of you guys. I scolded you for some little memory gaps in trig, and look at you guys. You guys are like, oh, I reviewed it. You guys clearly reviewed it. Because I'm like, what's the angle of this? And you know it. I'm very proud. I'm very pleased. Keep it up, guys. I'm really proud of you. On Wednesday, you should be getting a lot of papers back. I won't hoard your papers. I want to give them back. I'm not very strong, so I can't really carry this heavy backpack. And I'd rather make it lighter. To give you your papers back. You guys see how amazing this chalk is? I've been using it all class and it barely moved. It's really cool.
Dr. Bowler, on Friday, the yellow chalk. I think it's the best chalk I've ever used.
It is the best chalk. It's called Haguromo brand. Haguromo brand chalk. It is like gold to mathematicians. We will like fight each other over a box of this chalk stuff.
I did have one question.
Yes, sir.
Converting from spherical to cylindrical or vice versa.
Okay. So notice it's very clear how you can do it. We know how to go from any of those, polar, cylindrical, spherical, to rectangular, right? So let's say you want to go from cylindrical to spherical. Change it from cylindrical to rectangular, then move from rectangular to spherical. Right?
Yeah, I was just thinking. See, you mentioned that r squared is equal to rho squared, right?
Uh-huh.
So with that, if you do some weird math, you could set the two equations equal to each other since both are equal to x and y.
Uh-huh.
You could set like, what was it? R sine theta is equal to
I see what you're trying to do.
Yeah.
You're trying to like create transformation equations that directly transform from
that.
like
so
cylindrical to spherical.
So basically, I don't have to do the same work twice.
Yeah, it can be done. But will it create a kind of complicated result? Maybe, maybe not. You have to go find out.
Okay.
But yeah, I highly encourage you to go do it.
I have about an hour before my next class. That should be enough.
That's the right mentality.